Okay, so hello everyone, and welcome to the tutorial for the Simulink simulation for the dynamic analysis. So before I get to start to do anything, please, I would like you to download the MATLAB 2024 from the MathWork website. You can log in through the university account, and from there you can actually get the free license. Usually you get to have student license. When you do that, when you do the download, be sure that all the apps should be included. Don't uh, don't actually exclude anyone. I know that the size of the installation is going to be quite large, which is something like 25 gigs on your computer. But just remember that we are going to need all uh, uh, the apps to be downloaded within the package. So we're going to first download the file that's required for the simulation. So we can actually, I'm doing that now for Western Sydney Uni. Sorry for that, I should log in earlier. And using this account, unfortunately, I'm not going to be able to see my password, but at least you know my staff number now. Yep, we need to have the verification to be done. And yes, it's me. Okay, and yes, stay signed in. Okay, so we go to the website, we go to the subject of the 2035. We go to the week 7, PRACS for the week 7, and you can see that we have the document here and we have the zip file. So again, download them both. Okay, we'll go to the download file in my computer. That's the document. Also, it's going to go there. Okay, so I'm going to open this one directly, and I'm going to open the folder. I'm going to open the folder for the zip file. I can see that the zip file now is on the download section. I'm going to copy that, and shall go for. I made a folder actually on my C drive. I called it BH, or because actually the file is called BH, and I'm going to add the file there uh, with the full name. I'm going to much easier to make it a shorter name, like for example, I will call it the week 7 zip file. So that's week 7. Okay, and I'll leave it as a file. Now we go to the next step. We don't need anything now from the view. I get to start the MATLAB. Now it's taking time. It's happening on the other screen, but anyway, it will come very soon. Well, my computer actually is busy because I'm running many of the browser tabs. I have emails here, I have other things on the other side. But anyway, still opening on the other side. And here we are. Okay. So actually, you can see that because I was doing that from last time, so I already have it. But anyway, to find your directory, you click on this bottom, and you are going to go to this PC. You're going to double click on this PC, go to the PH, and you're going to select the folder, and now it's going to be updated. Should be updated. Still using the old one, VH. Select the folder. Ah, yeah. Now here we are. Okay, so you can see that I already unzipped the file yesterday, but I'm going to read it once again. So this is the new folder that we have. Again, to unzip the content of that folder to here, simply by typing here unzip. Okay, and you open a bracket. You can make a space. Open a bracket, put this sign, and it's not a bracket. Shift bracket. Yep. Put the sign and just write down week 7. 7, and close it. Okay, now here we are. Enter, and yeah, that's the correct one. Just enter. Okay, and now you'll see that this folder actually going to be unzipped. Yep. Okay. Now we come into the first one we're going to have is going to be the Pendulium example. Again, double click on that. You can see that the file here are neatly organized because we can double click on this one. You can simply do the sort by and select type. So you can see that each file is going to be under its type. We have the folder, we have the mat file, we have the live script, we have PNG files, and so on. Okay, now we're going to start with our first task. Actually, you can see that this one is on from the last time. Again, to close these files, again, to restart them once again with you. Okay, so we unzip this file, and now we're going to come to here. Looking for the first file is going to be ph start here, this one. Don't double click on the file, right click and click open. And you can see that in the live editor, we open this file. You cannot see actually the whole view, so we can simply double click on this bar, and now it's going to be much better to have a look. So I think that you remember this example we had multiple times during the tutorial sessions. We said that this will be a pendulum, which is actually going to be a link that connected at one point, and it's going to be swinging around the point O. At the same time, we're going to have the mass, which is concentrated at the bottom point here, the center point, which is going to be the mass centroid, and the mass is going to be pointing downward in this scenario. The total length of the bar is L. So the distance from O to G is going to be L divided by 2. The angle is theta with the x-axis, and here we're going to have the IO, and here we're going to have the IG. So you remember that the IO is going to be equal to 1 over 3 multiplied by the mass multiplied by the length square, while the IG is going to be 1 over 12 multiplied by the mass multiplied by the L square. We have a depth and height for the bar, and we have the length. So these are some of the parameters we should add. The omega, and we can calculate the value for the theta double dot, so it's going to be the angular velocity, angular acceleration. Now what we can see here that first we have to define our model parameter. So it's mentioned in this document that for the first case scenario, the P is going to be your last 3 digits of your student number. That's for the Western Sydney Uni students. Okay, and we're going to find the parameter to be calculated. So we are now at this case study, the one-link pendulums. This is the case study. These are the equation we're going to have. You remember we said that the sigma of the moment, we have the free body diagram, and then we have the kinetic diagram in this scenario. So the free body diagram will give me the moment to be equal to, for that case, is going to be the mass multiplied by that distance, which is the L divided by 2 multiplied by cosine of the theta. So the x value distance is going to be equal to L divided by 2 multiplied by cosine of theta. So this will be the moment I'm going to have due to the weight. And it's going to go to the clockwise direction. So that's why it's going to be negative here. And we have the b multiply, well, I must say b multiplied by the theta dot, which is the omega, and we have the lambda. We're going to explain that very soon. And on the other side is going to have the I alpha. Rearrange the equation, the alpha will be given with that uh, derivative equation. So yes, we started the Pendulium section, and we're going to work with that. These are the parameters to be calculated: the mass, the length, the height of the pendulum, and the width of the pendulum. And these things are going to be calculated automatically, but it's going to be actually this one for the moment of inertia about the center of the gravity or the center of the mass is going to be 1 over 12 multiplied by the mass multiplied by the L up to power 2. Okay, and for the other one around the point O, you have to calculate that if you are Western Sydney Uni student. The only difference is going to be that this one is going to be 1 over 3. The omega for this example is going to be constant and is going to be equal to 150 radian per second. The theta is going to be 30 degree. You are going to have you have to do the screenshot for every multi-domain model below, and please do not screenshot of your outcomes of the velocity and the acceleration. Uh, do a screen, sorry, the acceleration and the center of the mass of the pendulums. So, okay, so this will be the parameters we need to do for this example. Now we get back to here. We finish, we click on this part. Okay, and here we're going to have the new page that we are going to have the parameters we enter. So for you, you have to add p here. You have to add p over the 5, and the value for the b is going to remain the same, and this value is going to decide what will be the width and the height uh, of the bar in meter. I got to leave these parameters for me the same, but you have to change it. Now calculating for the IG and the IO. So these are the equation already built in, so you don't have to do it, but the computer will do it for you. Now we leave the value for the theta to be the same at 30 degree. That's what we have here, 30. Okay, you can enter that. And for this one, we need it to be as 150. So click here and type 150, or you can do it through the slider. Okay, so it's up to you. Enter, went to 150. The maximum velocity, I think, is 160. Now we can define what will be the motor and the gearbox parameter, which has already been defined here. But if you would like to change this value, you go to the reference and you can select a new motor for yourself. So it's all given here. The N of the gear is calculated as the omega N divided by the omega out. And this will be equal to the R out divided by the efficiency N. This value has already been fixed up, but if you would like to change it, you simply just put here and type whatever you want. Now, define some of the control system parameters, like the value for the constant TS is going to be given in seconds as 0.001. You can increase that or double that, it's up to you. And now we go into the local sub-functions only beyond this point to be changed. For example, compute the IG for the rectangular prism. And we just mentioned the equation for that. Okay, so the IG, as you can see here, is going to be equal to the length square divided by 12. That's in the different direction, but we mainly care about the x1, which is going to be the length square multiplied by the mass divided by 12. Okay, and now for the compute of the I about the desired frame using the parallel across axis theorem. And once again, the equation has been given to us, or built in actually here, so we don't need to do anything about that. Now leave this one open. Again, to go to the first page once again, creating the and simulating all the Pendulium models. To do that, we're going to click on that link, which is going to be opening one of the other files that we have here, the Explore of the Simulink. I don't want to open it from here because I can simply have a shortcut for it from here. I'm going to click on this one. And now we start with the multiple tasks toward building the Simulink. You don't have to actually create it because you already have blocks being done by the mathwork company that supplied us with this model. So you just need to follow the steps, and it's going to show you actually the model, and then you're going to use it. So the most important thing for us is that we need to know how to follow these steps and make the simulation process. So once again, I'm going to increase that to show you the steps. So once again, we have to apply the Newton's second law. Okay, so we came out with the final equation that the theta dot is going to be using this equation. That's what we mentioned earlier. It's all about the moments in the free body diagram and the kinematic diagram to get the value for the I alpha or the IO alpha. So step number one is load some of the model parameters into the MATLAB workspace. We did that, but let's bring it to here. First, we are going to click this button to run the code section. Click me. Now you can see that some calculation has been created on the side. So now we're going to make it clear. So to make it clear, I will come to here and type here clear to remove everything from the workspace. So just write down clear and enter. You can see that it's all gone. Now, I don't need to go to this one because already it's opened and we changed the parameter there. But I would like to bring back the fresh one to the workspace. So whatever the only thing we're going to do is just write down that that's what we need to bring. So you can simply actually copy that and paste it here. Control V, it's here, enter. Now you can see that we got the fresh value. So every time you would like to refresh the parameters, you have to clear, change the parameters, then come here and update it. That's it. Now you can type actually who's, which is going to show you actually what are these parameters here. It's going to bring the same thing we have here, if you can all see it, to here by write down WHOS. Enter. So we start to have the name, the size, the biology class, and the attributes. Now, we finished with the first part of updating the parameter. Second, we need to work with the Simulink. To find the Simulink, what we need to do is we need to click on the Simulink. Where you can find this one, it's not here. Simply you have to go home. Go home, click on the Simulink, and it's going to open a new window for us, which is the Simulink window. In the normal cases, if you don't have the things available for you, you have to simply do as what we've done with the Arduino by bringing the blocks and make a connection between them. Okay, at this stage, I'm not going to do that. So just keep this one open. That's the open window. Now, step number one is open the pre-baked Simulink model. So here is the Simulink model of the Pendulium. Does it look like does it look and respond like yours or not? So you can do the same thing while following the steps, but I don't want to do it right now. Simply, if I'm going to click on this one, this will make it work. Otherwise, you can bring the things here, but anyway, click on this one, and you will find that the model will work. Okay, did it open now? Not yet. Okay, I don't want to work with this one, but anyway, yep, it's working. It's opened. So it's going to bring you the model. Yep. So that's the model. We're going to check actually the result by using the output here. So everything, all the things has been built within Newton plant. We just brought the logs, we put the equations in. As I told you, once again, this is a quite advanced stage. I'm not going to teach you about this one, but I'm going to show you how it's going to work later. Now don't run anything. Next step is we are going to open the pre-baked Simulink link model for the MATLAB function blocks. So simply what we have is that we put code to calculate the value for the theta dot by using the equation that we derived earlier. So rather than using the core Simulink blocks to implement the expression for the theta double dot, the MATLAB function block can be alternatively be used. Now, once again, we can click here and just wait for the new model to open. So you can see it's just only one MATLAB function. Theta dot dot is equal to the function of the tau, b, m, g, l, I, o, theta, and theta dot. Okay, and then we just put the equation in and end. That's it. So that block is only going to calculate the value for the theta dot based on the parameter that we supplied. Step number 2A is going to be open the pre-baked Simscape model, and this is an alternative way of the modeling of the Pendulium Simulink, and rather than using the derived ordinary differential equation, we can simply use the Simscape block library from the Simulink, and for the Simscape will allow you to plug and play the real engineering components. For example, the Simscape has a block for the electrical motors, for the pump, for the batteries, for the PV arrays, and extra. For 3D mechanical system, the Simscape multibody library allows you to very easily assemble a model of the mechanical machines, and you can even translate the CAD files. Like you can make it on SolidWorks, then you can bring it to here. There are some tutorials available online about this process, but um, usually they are in different language. You can find the English language one. Anyway, again, to double click on this one to operate the Simscape model, and here it is. Okay, it's still uploading. Okay, now that's Simscape model. So what we can find here is that this is the damping plant that we had, and it's actually including the Pendulium. So I can double click on this one and show you what we have inside, but you can see what we've done is that we just simply defined the multiple blocks, okay, the solver configuration, the word frame, the mechanism configuration, and we just put everything in, and this will be fed by the parameters. Now, step 2B is going to be does the Simscape agree with the Newton drive model or not? So we can simply compare our Newton drive model against the Simscape model. Click on this one. Again, we're going to have another file that's doing the same thing. Now we're going to have another results coming from the Simulink. That's the comparison one. We're going to do this one very soon. Okay, so this will be the Simscape plant, and this is the comparison Newton plant, and we're going to have a comparison between both, and this will give me a sketch for the results from both. And finally, step number 3 is going to be the Simscape, means we're going to have a multi-domain simulation and designs. So in the Simulink Simscape, you can simply model the multi-domain engineering systems, parameterize the almost everything, and use your model to design a control system. And finally, you can automatically convert your Simulink control algorithm to a standalone C or C++ codes. Again, click on that one, and we are going to find the multi-domain controller. Okay, so once again, you can see that this is what we have for the command position. That's what we have for the control system. That's what we have for the electromechanical plant. That's the motor and the gearbox. That's the Pendulium system that we had earlier. And this is the discrete controller. Okay, so let's go back to this one. Now we have everything ready. We can start run them individually, but I prefer to go to the main page here. Let's start here one. You go back to the live editor and you can run the whole code. Now it's running and this will come to us with the pop-up screen that shows actually Pendulium is running. Should be coming soon. It's just taking its time. Wait a second, it doesn't work. I don't know what's happened. I'll try to run this one. Oh yeah. So now it's running the Simulink thing. They all has been run. And as I told you, this should actually give us the run for the first one. So anyway, I can start with them one by one and see how it's going to work. Mhm. Well, actually, it's not what I want, but I need this one here. Okay, so yeah, that's actually what I hate with the MATLAB. Sometimes it works perfectly, then suddenly it's not working. Um, this one doesn't have run. Actually, it should show me a 3D type model of the things working. Ah, yeah, that's what I'm talking about. So it's the last one, and you can see it's just moving in 30-degree up and down. Okay, so you can tell that actually that the inertia doing the work up and down. Okay, and we're going to have a look for the results soon. I can simply increase the time rate. Okay, now we've done with that, and we can replay it if you want again. Shouldn't be a problem. But now let's have a look for the output we have. Okay, plot the categories. 7 to the other side of the screen. Let's choose this one. will be removed in future release. Okay, just make it work now. Didn't get any value here. Okay, so no, no, that's not what I want. Okay, so just 1 second. Okay. Okay, so that's what I got for the theta 1 and theta 2 as a graph. Actually, that theta, that theta dot, but I would like to have the theta double dot here. Okay, so anyway, you can, well, actually, that's logically, they started high and then it's going to be drop, but I don't know why it's increased back once again in for the omega. So the omega started from 150, start to change in clockwise and counterclockwise direction until we have the end. So, yep, I'm going to close this one. Uh, Actually, I have the data inspector here. Mm, just 1 second. Oh, sorry. But once again, that's not exactly what I want. And also didn't show me any results. So anyway, theta and the theta degree. Okay, now let me check another one. Okay, so that was for this one. Let's check that one. So you can see that the value for the um, swinging is reducing now within the time. It wasn't as we saw it earlier when it dropped from 30 degree until now it's decelerating. So that means that the theta double dot is actually decreasing and going to zero, while the omega is also going to be decreasing, changing from clockwise to counterclockwise. So it should have positive and negative value. And we show that actually in the graph that we had earlier, which will be okay. Oh, now that's the point. I don't know why it start to increase in one direction. There's something wrong here. And it stopped in this position. Well, I'm going to double check about this one. So yes, that's the same scope that I had after running the work. Again, that's the value for the theta starting from 30 degree then start to go to minus 200 and going up, down, up, down. So now I don't know why instead of going to zero, uh, it's increased once again. It's went energetic once again for no reason. Okay, so that's something I need actually to have a look about. But anyway, we got the results. I need to check an expert with that scenario. Now let's have another look about the models that we also have. Does this one have an output here? The conversion between the command one and the actual one. It's told me about that. So that's the actual. Where's the theoretical? It seems to be that they are on the same line. Okay, so remember that should be for the theta double dot, and it didn't sketch actually the, oh, I'm going to hide this one. So they're actually compatible. So that's it. These are the value you need to copy and paste in your uh, report for this task. Okay, so yeah, I double click on all those side. What about this one? This one had. Yeah, well, actually gave me the same thing. Okay, yep. So that's it for this model. I will do the other model in a different video.